Hello, Chemistry 11. This is Mr. Chan. And today what we're going to do is we're going to talk about a topic called stoichiometry. Now, what stoichiometry is basically another practical application of the mole concept. Now, earlier on, remember when we talked about the mole, one practical application was to use the idea of molarity, where we found the concentration of a substance. Another aspect was, remember, we talked about something like empirical formula, which was the ratio of atoms in a compound. And we had molecular formula. So what stoichiometry is basically taking the idea of the mole, and what we're doing is we're studying the relationships between reactants and products. Now, so what we're doing is we're taking the idea of the mole, and what we're doing is we're combining it with balancing equations. Because when we balance the equations, the coefficients provide us with the proportion or ratio of each substance in a reaction. So when you balance the equation, let's say we had 2 Mg plus 1 O2 gives you 2 MgO. What happened is you had a ratio of 2 to 1 to 2, and the ratios are expressed in moles, atoms, or molecules, not grams. Okay, so when you balance the equations, what you're doing is you're providing a ratio between the reactants and the products. Now, one can think of stoichiometry like a recipe for baking or cooking. The balanced equation is like the proportions of ingredients for a recipe. So let's say, for example, we have 6 egg whites, 1 liter of whipping cream, and 600 grams of chocolate. That will provide us with 48 servings of chocolate mousse. Now, if we were to say, reduce this down to, let's say, 3 egg whites, we know that this will be reduced down to half a liter of whipping cream, 300 grams of chocolate, and that would give us 24 servings of chocolate mousse. And you know that because since the egg whites went down proportionally by 1/2, everything else goes down proportionally as well. The amount of whipping cream, the amount of chocolate, and the number of servings produced. If you keep this idea in mind, this is basically stoichiometry. But instead of using like grams and liters of whipping cream and chocolate, we're using things like moles or atoms of different chemicals like magnesium and oxygen. Okay, so just keep this in the back of your mind as we continue on with this. Now, in your notes, what you will see is you will see this particular chart, and I'm just going to pause it here to let you copy this down. So you can pause my video and just jot this down. All right, welcome back. Now, as you can see here, everything is pointing towards this starting moles. So it doesn't matter if you have a starting mass, or you start with a volume of solution, or molarity, or volume of a gas, you always want to start by converting everything to moles. Then you multiply it by mole ratio towards your ending mole, and then what happens is you can find your ending mass, your ending volume, or your ending molarity, by doing the appropriate calculations. Now, one thing I would like you to be aware of is this. Notice I have 2 volumes, one that is highlighted in yellow and one that is highlighted in blue. So notice, how do you approach moles from volume of a solution? You multiply it by molarity. And to go from moles to volume of solution, you divide by molarity. You contrast that to volume of a gas that's highlighted in blue. You divide it by 22.4 liters to get moles, and you multiply by 22.4 liters to get the volume at the end. So please make sure when you see the volume of something, you first have to say, is it the volume of a solution or volume of a gas? And that will determine how you approach the question and get to moles. Okay, now what I want to do is I want to go over a couple of examples with you just to show you what I mean. All right. Now, before I do that, notice the bridge between the starting moles and the ending moles is this mole ratio. And this idea of mole ratio is what we call stoichiometry. And this is from our balanced equations. Okay. So what I'm going to ask you to do is take a look at the worksheet that you have in your package. And what I want to do is I want to start off, I'm going to try question number 1. Okay, and then maybe I'm going to jump down to, oh, let's say, let's go down here. Let's end number 18 at the end. Okay, so number 1 and number 18. Actually, not number 18, I'm going to do number 19. Okay. Now, so let's do question number 1. It says, what weight of oxygen will be produced by heating 400 grams of potassium chlorate? Now, the first thing you want to do is we have our equation here. KClO3 gives you KCl and O2. So if we have, first thing we do is we have KClO3. Well, let me just put the rule lines here. Okay. So let's say we had KClO3 gives you KCl and O2. Now, the first thing you need to know is you have to balance the equation. So in this case, the balanced equation will be a 2 here, a 2 here, and a 3 here. Okay? Now we read the question. It says, what weight of oxygen? So in this case, you see the word weight of oxygen. So when you see weight, that means it's in grams. So here, if we were to break this down, this is X grams. Okay. And what are you given? It says 400 grams of potassium chlorate. Now, this is where you need to remember chemical naming. What is the formula of potassium chlorate? And in this case, that would be KClO3. So here you would have 400 grams. Okay, 400 grams. Now, do you need to worry about moles of, do you need to worry about KCl? The answer is no. Okay, so I just blocked this off because it just helps me focus on what I need to do. So what is the first step? The first step is to calculate moles, in this case, of KClO3. Okay, so the moles of KClO3, what we do is, so let me just get my periodic table out here. Okay, so whatever way you do it, you go, okay, so 400 grams times 1 mole of KClO3 all over the molar mass of KClO3. So K is 39.1 and 35.5 and 3 times 16. So that gives me 122.6 grams. of KClO3. And that gives me an answer of 3.2626 moles of KClO3. Now, in this particular case, the 122.6 is just the mass of potassium, chlorine, and oxygen combined. We do not worry about the coefficient, okay? We don't worry about that coefficient of 2. So our first step is done. Find the moles. So if we look back at our original sheet up here, I went from starting mass, which is up here, I went down to moles. The second step is the mole ratio, which is the balanced equation. So when I take a look at this, number 2, I'll do it in a different color. Use mole ratio. Okay, so what do I want for mole ratio? So looking at the balanced equation, I'll say if 2 KClO3 is equal to 3 O2, then what we do is this. I'll do it this way. We have 2 KClO3 over 3O2. That will be 3.2626 moles of KClO3 all over X mole of O2. Now, how do I know that I want O2? Because that is in the question. And if we do cross multiplication, okay, so in this case, we do cross multiplication here. All right, and you remember this from before. So multiply by 3, divided by 2. So I get an answer in this particular case of 4.8940 moles of O2. Okay. So looking at the second step, we use the mole ratio. Now we have our ending mole. Now, what does the question ask for? They want to find the mass of O2. So we have to go and find the ending mass. So what do we do last step? So step number 3, calculate the mass of O2. So what we do is we take our 4.8940 moles of O2, multiply it by 32.0 grams of O2, all over 1 mole of O2. I multiply by 32. I get an answer of 156.6 grams of O2. Now, that's basically the 3 steps. If I shrink it down here, step 1 is to find moles. Step 2, use mole ratio. Step 3, find what you want. In this case, we want to find the mass. Okay. Now, if you take a look at the answer, I don't know if I have the answer here. Notice the answer is 157. You might say, well, Mr. Chan, why? And the reason being is because of sig figs. There are 3 sig figs in the question, so you should have 3 sig figs in your answer. All right. Now, I'm going to show you a different example, but the idea is exactly the same, where you have to do the 3 steps. Number 1, find moles. Number 2, mole ratio. Number 3, find the answer. So let's take a look at question number 19. So question number 19, you have Al plus H2SO4 gives you Al2, SO4 brackets 3, and H2. So what you have here, if we balance the equation here, just like before, so we have, what is it, 3, 2, and 3. And let's set this up exactly the same. So looking at the question, it says, what volume of 4.4 molarity H2SO4 solution is needed to react exactly with 100 grams of aluminum? So in this case, we have 100 grams of aluminum and 4.40 molarity of H2SO4. Now, what is it asking for? It is asking for volume of H2SO4. So in this case, they want liters. Now, because the question doesn't ask for aluminum sulfate, I just cross it out. Doesn't ask for hydrogen, I just cross it out. So it just helps me focus on aluminum and sulfuric acid. Now, what might trip people up is they might say, well, Mr. Chan, we have numbers for aluminum and numbers for H2SO4. Which one do we start off with? Well, if we go back here, if we look at the H2SO4, whoopsie, notice they give me molarity, okay? So if I take a look back at this little table, if I had starting molarity like down here, to get to the moles, I would need volume. And notice I don't have that. Then I'm not given the volume. So this sort of automatically disqualifies H2SO4. Now, how about aluminum? Well, aluminum, we have mass. So in this case, if we had our starting mass, we can use molar mass from our periodic table. So that's what we can do. So in this case, first step, find moles of aluminum. So you have 100 grams of aluminum times 1 mole over 27.0 grams of aluminum. So you have 100 divided by 27. So that gives me 3.7037 moles of aluminum. First step. Second step, what you want is the mole ratio. And again, if 2 aluminums gives me 3 H2SO4, then what we have is we have 2 aluminums over 3 H2SO4 is equal to 3.7037 moles of aluminum all over X moles of H2SO4 times 3 divided by 2. So that gives me, in this case, an answer of 5.556 moles of H2SO4. Now, notice step 1 and step 2 of this question is very similar to step 1 and step 2 of the previous example. We wanted to find moles, and then we use mole ratio. Step 3 is where it's different. In this example, I asked for the mass of O2, in this example down here, the third step, what you wanted to do was what was the volume? So here, to calculate the volume of H2SO4, if we go back to our little chart, how do we find the ending volume? It says here we divide by molarity. So in this particular case, we take the 5.556 moles of H2SO4 divided by 4.40 molarity. And that gives us an answer of 1.26 liters. Okay? So what you can do is take a look at this question and notice even though the units are different, in this case we have grams, molarity, and liters, and we're looking for another reactant. Compare that to the first example where you had grams going to grams, you had reactants to products. Doesn't matter how this question is set up, notice the steps are exactly the same. Find moles, mole ratio, then calculate what you want. Here, find moles, mole ratio, and calculate what you want. Okay, so if we take a look at the answer for question number, I believe it was 19, I get 1.26 liters. Okay, so that's it for stoichiometry. It's basically another practical application of the mole. And the only new thing that you need to be aware of is this right here, this second step, where we're using the mole ratios or the coefficients from the balanced equations to go from one chemical to another chemical. All right, folks, thank you very much. Have a good day. Bye-bye.